All righty, welcome to Friday morning. We're going to do our usual thing. We're going to do some new stuff. We're almost there. We may actually finish today, depending on how many homework questions you have. I think that it might be a good idea to get it out of the way before weekend so that we can spend Monday reviewing because it's coming up quick. I think Tuesday's the test and then like Wednesday's the final. So bang, 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 it all comes to a close. So let's see. So we'll start as usual here. We've done up to this point, multiple integrals. We've got how you define them, how you do the curve to curve and number to number on the bounds. We've got that one before, yeah, polar. We did it in polar, and then we introduced the idea of the center of mass. So maybe I can just write something down here real quick. All these things are going to look like an integral over a region of some function dA. And you can either write that as like x1 to x2 and y1 as a function and y2 as a function, and that would be integrated dy dx. We've seen that if you want to write it the other direction, it would be like numbers y's and then functions. I know they look like the same notation, but if we write x1 of y, x2 of y, that represents that it's a function or a curve as opposed to just a straight up number, and that would be dx dy. So you could write it like that. And again, this is due to Fubini's theorem, which I'll at least mention and definitely not prove. Or if you prefer, you can write this as theta 1 to theta 2 numbers, and then curves r1 up to r2. And then your function you have to convert to r cosine theta and r sine theta for x's and y's. And then the big catch is on the end, you'll have r dr d theta as your dA, what they call like integration element there. And that extra r is something you got to remember. If f is a density function, then the integral is the mass instead of the volume. If f is equal to x times delta, you get what this thing is called my axis. And if f is equal to y times delta, you get m sub x axis. And so then if you put all that together, you can write it as the center of mass is my over m and mx over m. Hopefully that all kind of starts to make sense. If you start seeing these double integrals as being sums, then they look a lot like all the moments and center of mass stuff you calculated in your other classes, if you've seen that, which I think you probably have seen that in physics somewhere. So all that stuff sort of represents volume. And you probably should put that up here. Well, it's one of these things. It's like if maybe I should put one more little thing here, because it all depends on what that function is. So if you put in at delta, you get mass. If you put in these other things, you get these moments. If f is equal to 1, then the integral represents area of the region R. So it all depends on what you're integrating as to what the actual application means. So it's kind of nice. You just set it up once and you plug in different things on the inside and it gives you different meanings. And so this is where 13.5, it's basically the same thing, except now we can plug in something else and we get surface area. And how does that work? Well, let's see. We're going to do the usual thing. If you're not tired of Riemann sums yet, well, we're going to do one more here. So the idea is you have a surface up above. It could be a paraboloid, ellipsoid, it could be a sphere, it could be part of a cylinder. So you've got this surface up here, z equals f of x, y. So here's your surface. and you want to talk about the surface area of some of it, all of it. So you again say, well, I want the surface area, part of the surface area of this. Some of the examples we're going to do the whole surface area, but this is setup. So what we need to do is we want to say, let's find like the surface area of that region inside there. I know this looks kind of arbitrary, but the question is what's the surface area? Ah, good Lord. Go right slower. Surface area equals what? Of that shaded part. So what we need to do is we need to go down to our shadow again. So we can then here on the shadow region, and drop it down below. So we don't want to I don't want to do volume. I don't want to make it look like a volume, but we take the shadow down below in the region here, and we chop up the shadow region into our parts. Doing our regular Riemann sum chop up down here. So any of these little things down here will just look like, you know, delta x and delta y down in the shadow region. Now, what does that look like if you bring it back up into the region up at the top? So if I was to then reverse and take this back up to the top, this thing will get chopped up, but I'm just going to say, let's take one little piece here, that little piece right, the dark shaded part, which is above this little region down here below. And what does that look like? Well, it's going to be some sort of slanted, there's lots of little arrows going on here. It's going to be a slanted approximation here. It's not going to be, it's not going to be quite square, but we're going to use these things because they're very small squares to, again, approximate what these things look like. And this brings really a lot of stuff together, is that we want to talk about, like, we really would like to just do length times width. The problem is this will not necessarily be a rectangle anymore. It might be a parallelogram. So if you remember the volume, not volume, the area, because we're doing surface area, the area of a parallelogram is, well, if we knew the vector that pointed along this direction, and we knew this vector that pointed along this direction, probably shouldn't call it u and v, but the book does. It's not necessarily a unit vector. So if we knew these things, then in order to get the actual area, what we would be doing is we would scale each of these guys by delta x and delta y. And then what was the area for parallelogram? And the area was the length of u cross v. Back before, it's not, that's what we had from before. In our case, it's going to look like this. The area will be, the length of delta x times u. We're scaling this vector, whatever it is, by delta x, and then we're going to cross that with delta y dot, or times v. It's not dot, even though it's, that's a number. So it's the multiplication of these two cross the multiplication of these two. Now, this is all the theory, and it will come out into a very super nice equation. So if you want to like doze off for a second, you can. But where these things come from is the u is going to be the slope in the x direction. So this will be like the direction for the x slope, and the v is going to be the direction for the y slope. And so if you remember that way back when, it turns out that u is going to, so it's the direction for the x slope is going to be 1, 0, the x partial derivative. This is like the tangent line stuff. So it's like the tangent line in the x direction, the tangent line in the y direction. To do a line, you need a direction vector. So u ends up being this, v ends up being 0, 1, fy. So this is a repeat of what we had before. And so If we take all of that stuff and put it in here, then what do we get? We will get the cross product of delta x times the vector 1, 0, fx cross delta y times 0, 1, fy. And that will be my like area of the approximation to my surface area on just that little piece. So what I'm going to need to do is work all these out, do a Riemann sum, and add them all up. And it'd be nice if we can put it on the slide, so maybe I can expand it out here. As usual, very good. So this is the approximate surface area of the shaded part, with that shaded part from the picture. If you work this out, do the cross product and find the length, and I'm going to leave that out because it's not too hard to do this cross product. But then you do the length, you'll end up getting the square root, maybe not surprising, of 1 plus fx squared plus fy squared. And then you're probably wondering about these, like where the delta x and delta y. Well, those I can factor out when I do my length. So this will be times delta x times delta y. Ooh, that looks pretty good. Because this looks a lot like what we did before. This is like my delta A. So if you end up taking the sum, and then you take the limit, i.e., you do your calculus stuff, then this turns into be a really nice integral. This will be dA. We'll have a double integral of this thing. It kind of looks like a length. You had 1 plus the derivative squared, but now you have like 2 derivatives. So it's kind of like length in both directions to give you that little area there. And so dot, dot, dot. Next slide, we end up getting the surface area formula. So now I got to wake back up. Is the double integral over the region of 1 plus the x partial derivative squared plus the y partial derivative squared dA. So that's the formula. So there's a new one. When we had a 1 in there, it gave us area. If we had delta in there, it gave us mass. If we had delta x, delta y, we ended up getting different things. So now we put this integral on the inside, or this integrand, the square root, and we get surface area. So it's pretty nice. Once we get the integral set up, we don't have to change all the bounds and everything. We just change the inside and we get different answers. By the way, the notation for this is super shorthand, but we won't use it very much. But the notation is the double integral over the region ds. That's it. That's all they write. So in physics, if you take your higher math stuff, start seeing things like flux, and you'll end up getting these real short formulas that you're like, what the heck does that even mean? And you have to unravel it all the way back to go, oh, that's what it means? You just take these derivatives and plug it in? Yes. That's it. Oh, well, why didn't you tell me, why do you do this? This is like confusing. Well, yeah, that's what we do in math and physics, is we make it look confusing so that we scare people away or something. We're not very nice. All right, enough babbling. Let's do some examples here. And we're going to do 2 classic examples, just the surface area of a sphere to start off with. And maybe you already know the answer, but if you don't know the answer, then this will be the derivation of it. It's in the book, it's in lots of tables. So we're in for a treat. So we write down our sphere. So that's x squared plus y squared plus z squared equals, I don't really want to use r because we've been using r over and over and over. We need another letter for the radius. I think a is not that one to do. So we have a sphere centered at the origin of radius a. Might as well center it at the origin because if you change the surface area, you can move it. Okay, so surface area of the sphere. What we're going to end up doing is we're going to just do the top half, and then we'll just double that answer. So we'll take our sphere, oops, or hemisphere here. And so we're just going to say we're going to double this one, double this answer. And so this is A, all these directions. So in order to set this up, I'm going to need my function, my f, and I'm going to need to know what the shadow region looks like down below in order to set up all of these things. So the first one to get the function is I solve for z. So I have my equation x squared y squared z squared equals a squared. So I bring everything over, get a squared minus x squared minus y squared. And then when I take the square root, I'm going to take the positive square root, and that'll give me the top half. If I take the negative square root, I'll get the bottom hemisphere. So there's my function. And then what about the shadow region down at the bottom here? Shadow will look like a circle. And that's all. I'm going to be taking this integral with this square root and all these partial derivatives and stuff in it over that region there. And that will give me the surface area of the hemisphere, and then I'll double the answer. And I'll have the entire surface area for the sphere. So let's get the setup first by finding the partial derivatives here. So f sub x, I might want to rewrite this as a squared minus x squared minus y squared to the half. Might be easier. So my partial derivative will be, I'm going to need to move it a little bit. F sub x will be, take the derivative of that. So it's 1/2 a squared minus x squared minus y squared to the negative half. And then I multiply by the derivative of the inside, and you get minus 2x. The a squared and the y squared don't have x's in them, so that partial derivative will be 0. So if I clean it up just a little bit, I get negative x, the 2's cancel. The negative 1/2 power means put it on the denominator as squared root. Square root. So negative 1/2 power means square root in the denominator. So we get that as our fx, and then fy will be the same, except so 1/2 comes down, a squared minus x squared minus y squared, multiply by the derivative of the inside, and here's the part that changes, is we get minus 2y, because now I'm getting a y here. And maybe not too surprising, I get minus y, I get very similar idea, a squared minus x squared minus y squared. So those are my two partial derivatives that I need to square, add to 1, and then take the square root, and then integrate over the region. So we go to the next one here. Recopy some of the stuff. So my surface area will be the double integral over the region of 1 plus negative x over the square root of 1 plus 1, a squared minus x squared minus y squared squared plus negative y over the square root of a squared minus x squared minus y squared So I'm just plugging in fx and fy into the equation. Okay. Maybe just do a little bit of algebra here. I'll get 1. Please square everything properly. X squared over a squared minus x squared minus y squared, and then y squared. So all the negatives get squared out. X squared minus x squared minus y squared. So if I put this together, I'll get square root of 1 plus a squared minus x squared minus y squared. And I can put that in one denominator, x squared plus y squared. And actually, why don't I just get a complete common denominator here? So I have to multiply this 1 in order to get the common denominator, a squared minus x squared minus y squared over a squared minus x squared minus y squared for that 1. Put the common denominator together, and what are you going to get? You're going to get the square root of a squared minus x squared minus y squared. But what's going to be on the top? The top will be a squared minus x squared minus y squared plus x squared plus y squared. So you just get a squared dA. And therefore, so the surface area will be the double integral over the region. I can take the square root of the top, which is a, over the square root of the bottom, which is a squared minus x squared minus y squared dA. So there's at least the setup. And I'll just recopy that on the next slide. But it's just plugging in the partial derivatives, doing the algebra, getting the common denominator, taking the square root of the top and the square root of the bottom, and so we get down to that. Recopy here. So a over x squared dA. Now what you have to figure out is, how do you want to do this? Do you want to do this as dy dx, or do you want to do it as dx dy, or do you want to do it as r dr d theta? You have to decide, and you can really do any of them. I'm going to set up the first one there just to see what it's going to look like. So my shadow region again looks like circle. Here's A. So if you wanted to do this with respect to, say, dy dx, then you need y between two curves, and you need x between two numbers. So figure out what the top curve is, you figure out what the bottom curve is, so that'll be y. And then maybe it's not too hard to see that x is going to go from minus a to a. So what are these curves? So the equation of this circle is x squared plus y squared equals a squared. So now I'm down in the two-dimensional shadow. So if I solve for y will be a squared minus x squared, and then I'll get plus or minus the square root of that. And the top is the plus square root, and the bottom is the minus square root, just like for this hemisphere thing. So I get minus the square root of a squared minus x squared, and positive a squared minus x squared. And so this integral under that setup will be, okay, the integral from minus a to a of the integral from minus the square root of a squared minus x squared to positive a squared minus x squared of a over the square root of a squared minus x squared minus y squared dy dx. Oh, really? That's great. How do you do that? How do you do that? I don't know. Can you solve this? So you have to kind of go back to Calc 2. Maybe it's a trait substitution or something in the table. It's not going to be a straight up u substitution because I try, the u is the inside and I don't have the derivative to make this balance out. I don't have a 2y in here. I don't have a y in here to balance it out. So it's definitely going to be some sort of trig function or inverse trig function or something kind of ugly. So this is a correct setup, but that doesn't mean it's going to be helpful in actually solving it out. So what do? Well, maybe that one led to a hard integral. I bet that this one also leads to a hard integral as well. set it up, really the only thing that's going to probably change is the X and Y's change position, but the makeup of it is going to be difficult. So the thing is to recognize that this is a circle. And every time you do circles, polar is really the way to go. So it should be that if we set this up as a polar integral, we will be in much better shape. Plus, it's a sphere, so there's probably a pi in the answer somewhere. And I don't see it right off the bat. So let's convert this to polar. It's good practice anyway. So our shadow region here again, it's a circle, it's supposed to be. The undo function is my term. A. If I write this in polar, then that means that R is between two curves and theta is in between two numbers. And because it's a circle, this is nice. The radius is between two functions. So you start at the origin and you move out on the radius until you hit the inside curve, and there is no inside curve. So I'm going from 0 radius out to the circle. And again, the equation of the circle in polar is just R equals A. So R equals A is the circle of radius A. Radius. So that's super nice. And theta wraps all the way around. So it's going 0 to 2 pi. We also have the fact that x squared plus y squared is r squared. So in my integral, I guess I'll write it down one more time, but I have the double integral over r of a over, and here's where I'm going to slightly write the bottom differently. It'll be a, if I factor a minus out of x squared and y squared, it's going to look a lot nicer. So it was a squared minus x squared minus y squared, but I factored this minus out. And if I do that, then I can convert everything over here in the polar setup as the integral from 0 to 2 pi d theta, the integral from 0 to a dr. This will become a over the square root of a squared minus r squared. And then my formula always has this extra built-in r. So the dA becomes all this stuff. The integrand, I put in x squared plus y squared is r squared. And then the bounds are gotten from parameterizing my polar. I don't know if this looks any nicer, but it is way nicer. The bounds are all nice, and we have an r squared, and we have an r. So probably I want to do u equals a squared minus r squared. Du is minus 2r dr. So when I plug this stuff in, I'm going to leave the bounds off for just a second. This will become the integral of a over the square root of u, and then the r and the dr will give me negative 1/2 du. Well, I'll just put the d theta, because then I'm going to calculate the inside. So this is now really nice, because this is u to the negative 1/2. So how do you integrate that part right there? So the integral, I'll have negative 1/2 a u to the negative 1/2 du. So that'll be this inside integral here, just like we're doing in Calc 2. So this will be u to the 1/2 over 1/2. So this will be negative a u to the 1/2. I divide by 1/2, and that cancels my half out. So I just get that. So this will be, then I can put these bounds here. I can plug the u back in. So that's minus a times a squared minus r squared to the 1/2. So it'll be minus a squared minus r squared to the 1/2. And I can put my bounds back in, 0 to a d theta. And if you want to write that as r equals 0 to r equals a, it's not a bad idea to remind you. Okay, plug them in. So we get the integral from 0 to 2 pi. We'll have minus a times. When we plug in a, what happens? We get a squared minus a squared. So that's 0. If we plug in 0, we'll get a squared to the 1/2, which is just straight up a. So that's when I plug in r equals a. This is when I plug in r equals 0. I'll get I'll get 0 for the first one, and then a squared minus 0, so a squared to the 1/2. So I end up just getting the integral from 0 to 2 pi of a squared. Negative a times negative a. So you can do this. There's no, you just integrate that up to a squared theta, plug in the 0 to 2 pi, and this will be 2 pi times a squared. So to get the final answer, wish I'd left a little more room here, I double that so that the surface area for a sphere is equal to 4 pi times the radius squared. And if you knew that formula, boom, there it is. It comes from doing a double integral and changing it to polar. That's where you get your 2 pi from. And lo and behold, like before, we got 4/3 pi r pi times the radius cubed for the volume. Now we have the surface area 4 pi a squared. Ta-da! And most of the stuff in your other books you can derive using calculus. If you're bored sometimes, pull out your tables and say, why is that true? Let's do the work. Well, I would do that. I don't know if you guys would do that. Maybe someday. Maybe someday. All right, let's do one more before we break. Maybe we should. I don't know. No, break time. Let's do break. We'll see you at 8:10. We'll do the surface area for a cone, and then we'll talk about homework problems. Go from there. So see you at 8:10.